Click on the Add button next to the Component section. Under the drop-down, and you should be able to find the lock-on component. Let's add it to our actor. As simple as that, our component has been added. Any behavior we add to this component will become available to our actor. It's time for a challenge. Locking onto enemies is not the only action the player will perform in our game. They will be able to perform actions from rolling to blocking attacks. For this reason, I want you to create 5 additional components. Here are the components that you should create. 2 things worth mentioning. Make sure the components are created inside the public folder. Secondly, the components should be placed in the correct directory. For your convenience, I provided which folder each component belongs to. We have 2 components that will go inside the character folder, and the other 3 will go in the combat folder. We have a component for storing stats, a component for handling player actions, such as rolling, another component for handling combat, and a component for blocking attacks, and lastly, a component for detecting enemies during attacks. If some of these don't make sense, don't worry. We'll be working on them as the course progresses. I just want you to create them now before we get to them. After you've created these components, go ahead with adding them to your player. Alright, go ahead with finishing the challenge.
Okay, we are back. Let's create some components. So we have another stats. We have character stats. Characters stats component. Oops. This is the stats component. Then we have player actions. Player actions. Characters. Then we have 3 combat components: combat, block, and trace. Combat component. Block component. Public, combat, block, and trace. Trace component is also combat. Okay. Oh. Then you're supposed to add them.
3 will go in the combat folder.
We have a component for storing stats, a component for handling their
Actions, such as rolling, another component for handling combat, and a component for blocking attacks, and lastly, a component for detecting enemies during attacks. If some of these don't make sense, don't worry. We'll be working on them as the course progresses. I just want you to create them now before we get to them. After you've created these components, go ahead with adding them to your player. Alright, go ahead with finishing the challenge. Best of luck to you.
We got stats. We got player actions. We got combat. We got block. We got trace. Okay. Save, compile.
Time to go through the challenge together. It'll be pretty repetitive. At the top, go to Tools, New C++ Class. Select the Actor Component option. Make sure the class is public, and then set the name to Stats Component. Let's change the directory to the public/characters folder. Public. Our player. In total, there should be 6 components, including the login component we added at the beginning of the lecture. Awesome. We have our components ready to go. While we're not going to work on each of them immediately, it's nice to have them all available from the beginning. Go ahead with compiling the blueprint and saving the file. In the next lecture, let's work on locking onto the enemy by adding an input action. In this lecture, we're going to add an input action to activate the lock-on feature. We've got a component for handling the behavior of locking onto the enemy. Unlike before, we aren't going to write the logic with blueprints. We'll just jump straight into C++. So, let's define a function that'll start the process of locking onto an enemy. In Visual Studio, open the declaration file for the lock-on component. In this class, we're going to add a function called startLockOn. Let's add it below the protected section with the void keyword as the return type. Next, let's add the uFunction macro to the definition. This function should be exposed to our blueprints. Our components shouldn't really act on their own unless they absolutely have to. Keep in mind we're using C++ so that we don't have to clutter our blueprint graph. At the same time, we don't want everything to be directly inside C++. We should give the opportunity for anyone else to understand what's going on. To achieve that goal, we can define functions that are readily available from our components. Then, we can call them as needed from our blueprints. It's very similar to what Unreal does with the third-person blueprint. Inside the macro, let's add the blueprint's callable specifier. Visual Studio is going to complain the function doesn't exist. Let's generate it. Great. Inside this function, we're going to do some logging. If we're able to see the log in the output, that'll verify the function is running. Let's add the UE log macro. The category will be log temporary. Next, we're going to set the verbosity to warning. Technically, we shouldn't be throwing warnings unless we actually have a warning. However, it's helpful to change the color of our log to help it stand out from the rest of the messages. Unreal tends to produce a lot of messages in our logs, so it can be hard to find it during development. After setting the verbosity, let's set the message to the following with the text macro. Log on started. Cool, that's all we'll need for the component. The next step is to call this function the moment the player begins locking onto an enemy. The question is, when should that happen? We shouldn't force players to automatically lock on. Instead, they should toggle that feature when they press a key on their keyboard. Unreal has a feature called Enhanced Inputs, which you may or may not be familiar with. It's a relatively new feature introduced in version 5.1, so I won't assume that you're aware of it. The Enhanced Input System is a feature to help us detect an input from game controllers. It's incredibly feature-packed, such as detecting dead zones or filtering inputs. To use the Enhanced Input System, there are two files we're going to need. First, we need input actions. Input actions are files for storing the types of actions that can be performed by the player. Examples would be running, crouching, jumping, or attacking. For each action your player will perform, you'll need a corresponding action file. On top of describing the action, input action files have configuration settings for the types of values that can be produced. For example, let's say you're creating an action for movement. If your game is played on a gamepad, you may want to consider the intensity of a joystick. Pushing the joystick lightly in a direction should cause the player to move slowly, whereas pushing it firmly can force the player to move quickly. Other times, you may just be interested in checking if a button was pressed regardless of whether it was lightly tapped or not. The second type of file you'll need is an input mapping context. This file is a collection of all the possible input actions that can be performed by the player. This feature is incredibly helpful for games where gameplay can suddenly change. For example, if you have a game where players can traverse land, water, and air, each environment may have different types of actions. Jumping is something you should be able to do on land, but not something you should do while flying a plane. That really wouldn't make sense, would it? With these two files, you can easily start adding input for your game. By using the third-person template, most of the work to set up the enhanced input system has been configured for us, so we can just build on top of it. Let's switch over to Unreal. Open the content browser and navigate to third-person/input/actions folder. As you can already see, there are 3 actions for jumping, moving, and looking. The look action allows the player to look around the camera. We're going to add an action for locking onto the enemy.
Let's look at this. So this input action has no description. Value type axis 2D. Move axis 2D, jump, digital, Oh, it doesn't show this one. Put it here. Got another bot. No trigger. Okay, let's indulge.
To add a new input action, right-click in an empty area. Under the input menu, there's going to be an option to create an input action. Click on it. Unfortunately, my screen cuts out the option, but it should be available as input. The file will be called IA_lock_on. The letters IA, which is short for input action, are a common prefix to add to input action files. We'll be following this convention throughout the course. Unfortunately, my screen cuts off the option, but it should be available as input. The file will be called IA_lock_on. The letters IA, which is short for input action, are a common prefix to add to input action files. We'll be following this convention throughout the course. After adding the file, we can leave it as is. The default configuration settings for input actions work for our action. However, I do want to take a moment to view one.
Here we go. Okay.
Important setting. Double-click on the file to open it. There are many settings for configuring how this action is triggered. The setting we care about is the value type. When this action is performed, a value can be generated. Unreal gives us the option of configuring the type of value produced through the setting. By default, it's set to digital boolean, which can be used to tell us if an action was pressed or not. There are 3 more options. The Axis 1D option is useful when we want a value that goes one way or the other. An example would be a slider for the game's value. Up next, we have the Axis 2D option for producing values on a 2D dimensional plane, such as movement. Lastly, we have the Axis 3D option for producing values in a 3D world. For our purposes, the digital boolean option works perfectly. We just need to know if the player wants to log on or not. So, close the file and let's move on to creating the mapping context. This file already exists. If we move up one directory, we'll find a file called imc_default. Let's double-click on it. Let's add our action to this file. Under the mapping section, you'll find a list of other actions added to the file. To add our action, we can click on the plus button.
Okay. We do log on.
Going to be an empty slot where we can click on the drop-down to view a list of available input actions from our project. Select the log-on action from the list. After selecting our action, we can click on the arrow to the left of the drop-down. The next step is to bind a key to the action. There are 2 ways of adding a binding. Firstly, we can click on the drop-down for a list of possible inputs. As you can see, we can select buttons from popular game controllers, touch devices, or use input from a keyboard. Alternatively, we can click on this keyboard icon. By doing so, Unreal will listen for a key press from our keyboard. Let's use the Tab key. After pressing a key, it'll automatically find that key from the list of options. Perfect. In addition to setting the key, we can click on the arrow button for more options. You'll notice that some of the options are similar to the options from the input action. We have the ability to override the existing options with our own. The main difference is that these settings will only apply to the action within this context. So, if you don't want some settings to apply to every context, you can configure them from the context itself. We don't need any of that, so let's just save our work.
Oh, it wasn't visible, was it? Whoops, I should have brought it here. Now it's visible. I created this new log-on mapping, which I created earlier. I was able to select it from the list, and then I can assign which button press triggers it. So the keyboard here, I pressed this button, then I pressed the tab key on my keyboard, it detected it. Then I pressed add to add another way to trigger it, this time from the gamepad. So I pressed the right stick to assign it to that. Now we're gonna save. And now,
After adding the input, we can start using it. Open the content drawer. Navigate to the third-person blueprint, which can be found in the third-person/blueprints folder. Since the third person already sets up the enhanced input system, there are examples we can look at. Let's look at the jump.
Jump.
Example, which can be found near the bottom of the blueprint event graph. Look closely, we have an event called Enhanced Input Action, IA Jump. Unreal automatically creates events based on the action's name. To prove it, let's actually delete this event. Next, let's re-add it by right-clicking and searching for the action by its name. We want the one that says Event. If we click on this option, we get the same node. Let's expand it. There are a few pins available.
What's this jumping function? Where is that coming from? Started, jump, completed. That's it. Okay, so we delete this. And then we search for IA event jump. Started, completed.
To use. Let's go through some of them. Firstly, we have an execution for when the event is triggered and continues to be triggered. However, it only gets triggered when all conditions are met. If you have an input action with a few conditions, you can be guaranteed that all those conditions are met for this pin. Next, we have the started pin. This pin runs when the action is triggered for the first time. The difference from the triggered pin is that it only executes once, whereas the triggered pin can continue to get executed as long as an action is performed. Afterward, we have the ongoing pin, which is similar to the triggered pin. However, one major difference is that not all conditions have to be met for it to run. Then we have the canceled action for when an action is canceled before all conditions are met. Lastly, we have the completed pin for when the action was successfully performed. There are additional pins, but we're not going to use them in this course, so I'll just spare you the explanations. Let's hook this event node to the jumping function. Connect the start pin with the jump function. Next, connect the completed pin with the stop jumping node. So that's how the enhanced input action system can be used in our games. So to finish off this lecture, let's try a challenge. The goal is to call the start-to-log-on function. Before doing anything, you should compile your project's codebase. Our function was defined, but we didn't compile our project. So if you want to use the function, you should compile it first. Once you've compiled,
Cannot compile this. Look, where does this have an error? Did I mess something up? It's crazy. Oh, did I accidentally switch this, huh? Crazy. And I noticed now even. So this should work now, right? Whew. Okay. Caught myself making this silly mistake accidentally. Okay. Save all. Go to the main level. Save all.
About it, add the event node for the IA lock-on action. Lastly, I want you to call the start lock-on function. However, I won't tell you what pin to use. It's up to you to decide what pin should cause the function to run.
Okay, so we add another event to the player. Player is this one. Log on. It's called a group or something. Comment. Comment to selection. Okay. So first we do IA lock on. And then decide what pin to use. Start lock on function. Start lock on component. Lock on. Started, right?
Based on what we just talked about, this function should only be called once.
Let's see if that actually works. Third person, start, tab. Do you have any logs? Well, let's see what this
There's
is.
no need to repeatedly call it, so choose an appropriate pin. During this process, you may also need to grab a reference to the lock-on component. Keep in mind, our function is not available directly from the blueprint. It's available via a component. So you'll need to grab a pointer to the component before being able to call a function from it. Once you've done that, be sure to compile and save your work before testing. If you did everything right, you should see the log message appear in the console when pressing the tab key.
Which key?
Once you've done that, be sure to compile and save your work before testing. If you did everything right, you should see the log message appear in the console when pressing the tab key.
Console.
Alright, good luck and take on the challenge.
Output log. Lock on started, right? Output log. Good luck. I think that worked.
Welcome back. So let's quickly compile the project so that the function is available from our codebase. Great, let's head on over to our blueprint. In an empty area, right-click and search for the IA logon event. Add it to the graph. Once added, let's drag the logon component next to the event node. We have to do this if we want to be able to call the function. Let's drag out from the node to grab the start logon function. Lastly, let's connect the start pin to the execution pin of the logon function. We only want this function to be called once. There isn't a need to continuously lock onto an enemy. So the start execution pin is our best bet. Let's compile and save our work. Now let's head on over to our map. Before we play our game, let's make sure the output log window is active. It should be right next to the content browser window. Our log will appear in this area. Great, let's play the game. Once the game is active, we can press the tab key. As we do so, the log should appear. Awesome! We've successfully added the input action for locking onto an enemy. In the next lecture, let's work on scanning the map for enemies to log onto. In this lecture, we're going to use Unreal's tracing feature to help detect enemies within our vicinity. The next step in our journey to logging onto enemies is to detect them. When the player wants to log onto an enemy must be nearby for the log-on feature to activate. They shouldn't be able to log on an enemy that's far away. For this reason, we should check for nearby enemies before doing anything else. In the resource section of this lecture, I provided a link to a feature called tracing. Checking for nearby actors is a common requirement in game development. So Unreal has a specific feature to help us detect.
Reach out to your levels and get feedback on what is present along this line segment. You can use two endpoints, start and end location, reporting any actors that it hits. Okay, raycasts or ray traces. We're doing ray tracing. You can either get just the first thing or everything hit with a ray.
detect objects called tracing. Scroll to the Using Shape Traces section. You can think of tracing as lighting a flashlight. In the real world, if we want to see what's in front of us, we would point the flashlight in the forward direction. If we wanted to see what was behind us, we should point it in the backward direction, so on and so forth. Tracing works in a similar fashion. They are invisible lights that can help us detect an object. If you look at the image, you'll see an example. The tracing system turns green when it collides with a rectangle shape. Otherwise, it's red when it doesn't detect anything. The first step to using the trace system is to add channels to the objects we want to detect. A channel just refers to the category a physics body belongs to. Think of it like this. In the real world, we have three categories for the states of matter, which are solids, liquids, and gases. The walls in your home are solid. If you were to attempt to press your hand against the wall, your hand wouldn't go through because your body and wall are solid. However, if you press your hand against a pool of water, your hand would be allowed to pass through it. This idea applies to our games. We can determine what categories our actors or components belong to in our game. Not only that, we have the power to determine whether they can collide with one another. Let's head on over to Unreal. Open the boss blueprint from the characters folder. Click on the capsule component. This component is responsible for detecting collision with other physical bodies. Under the Details panel, search for a setting called Collision Preset. Let's expand the setting. As you can see, there are multiple categories or channels to choose from. We can fine-tune how the component interacts with other channels. Overall, channels are pretty powerful. You'll notice that we can't configure these options. That's because the current value is set to on. If you want to configure these settings, you'll need to change the setting to custom. Let's do that. I'm gonna be honest, we shouldn't really tinker with the default channel settings. Instead, it's recommended to create your own custom channels, which is really easy to do. At the top, navigate to Edit, Project Settings. Go to the Collision subsection under the Engine section. Click on the New Trace Channel button. We can give our channel a name. Let's call it Fighter. This channel will be dedicated to characters that can fight each other. After setting the name, we can apply a default response. The response refers to the object this channel will respond with to another object. Something to be aware of is that channels are applied to all actors, from walls to characters. So we have an opportunity to configure how this channel is configured on them all at once. The two most common options are block and ignore. Block tells Unreal that the object should be detected. On the other hand, the ignore option will allow the object to be ignored during tracing. By default, we want to set this option to ignore. That way, every object isn't a fighter. We must manually specify that a specific actor is a fighter. So let's click Add to add this channel. Great, let's close this and then compile our game. Next, head back to the boss and compile the blueprint. The channel may not become available until you recompile everything. If we look at the channels again, the fighter channel should become available. Let's change it from ignore to block. Great, let's compile and save our changes. We've successfully added a channel for fighters. Now here comes your challenge. The boss is not the only fighter in our game. Our player is also going to be a fighter. While the boss won't be able to lock onto the player, they'll be able to damage them. Therefore, they'll need the fighter channel. We'll use the fighter channel during combat. It won't just be for enemy detection. So open the third-person blueprint. When you have it open, click on the capsule component. Lastly, update the channel settings by setting the fighter channel from ignore to block. That should be pretty simple, so go ahead with the challenge. Alright, let's do the challenge together. If you haven't already done so, open the third-person blueprint from the third-person/blueprints folder. Next, click on the capsule component. This component is responsible for detecting collision, which is why we're modifying it. Search for the collision preset setting. We're going to change the setting from pawn to custom. That'll allow us to modify the fighter channel. Change it to block. Lastly, compile and save your work. Fantastic. With that step out of the way, we can start performing tracing with our code. We'll handle that step in the next lecture. In this lecture, we're going to start tracing enemies to detect them by using C++ code. Here's what we're going to do. We're going to draw a tracing shape. If the enemy collides with our trace, we'll consider them to be within distance of our player. In Visual Studio, open the lock-on component C++ file. We're going to be working from within the start lock-on function. Right before we log a message, we're going to run a function called getWorld. Tracing is a feature not specific to actors. Any class can perform tracing. For this reason, the functions for performing tracing are outsourced to the world object. The world object represents our level. At the moment, our current level is the third-person map, so that's where tracing will be performed. After this function, let's chain another function called sweep single by channel. Unreal offers multiple functions for tracing actors. In this example, we're using a version of the function that finds the first collision as text. In some cases, you may be interested in grabbing all actors detected within a collision. In that case, you can change the word single to multi. However, we're only interested in locking onto a single enemy, so I'll change this back to single. Alright, what about the word channel? As you might suspect, this function can be used for detecting actors within specific channels. Specifically, this function is only going to return results where the channel is set to block. Luckily, both our player and boss have this channel. If you hover your mouse over this function, you're given a list of parameters. There are quite a few of them, so let's go through them. The first parameter is called outHit. The word out carries a lot of significance. In C++, functions are limited to returning a single value. If we look at the return value, it's a boolean which tells us if the sweep function was able to find a result. However, that's not the only thing we're interested in. We want the actor that was detected by our trace. For this reason, C++ offers the ability to modify a variable outside of a function. It's common practice for parameters to start with the word out to let other developers know that the variable you pass into this parameter will be modified. This parameter will contain the result hit by our trace, which we'll want. So let's create a variable to store the result. Above the function, define a variable called outResult with the fHit result type. Make sure the type matches the type from the function's parameters, which you can verify again by hovering your mouse over the function. Let's pass this variable into the function. The next two parameters are the location of our trace. Our trace requires a starting point and end point. For locking onto an enemy, we're only interested in detecting enemies within a specific range. To do this, we're going to use a spear. There really isn't a reason to launch our trace across the map. For this reason, the starting and endpoints will begin directly at the player's location. To get the player's location, we'll need to access the actor. As a reminder, we're using a component. Components and actors are not the same thing. Components are always attached to the actor. So to grab the actor a component is attached to, we can use a function called getOwner. Let's define a variable for storing the location. Below the out_result variable, define a vector variable called current_location. The value will be the function getOwner, getActorLocation. The getOwner function is available on all components. It'll return the actor that has the component. In our case, that would be the player. From there, we have access to the functions that are normally available on the actor, such as the getActorLocation function for grabbing the player's location. Let's pass this variable into the sweep function as the second and third parameters. But next we have to provide a rotation. There isn't a reason to pass in a special rotation, so let's pass in the following: Quaternion identity. A quaternion identity is just a fancy word to say that an object has no rotation. Instead, its rotation is aligned with the current world. You can use this static variable whenever you don't care about the rotation of your collision shapes. The next argument is the most important argument, which is the channel itself. If you look at the parameter list again, the data type is eCollision channel. Whenever a type begins with the letter E, that indicates an enum. This enum contains a list of all the Unreal channels, including the pawn channel. Type the following: eCollision channel : ::. After typing those characters, we're given a convenient list of channels that correspond to the channels from Unreal. The question is, which one should we use? Our fighter doesn't appear on the list. Believe it or not, it actually does. Behind the scenes, Unreal assigns our channels to a number. To find out that number, we'll have to look at the configuration settings. Over to the Solution Explorer, open the config folder. Inside this folder, open...
What? Where is this?
To find out that number, our fighter doesn't...
Solution Explorer, okay.
appear on the list. Believe it or not, it actually does. Behind the scenes, Unreal assigns our channels to a number. To find out that number, we'll have to look at the configuration settings. Over to the Solution Explorer, open the config folder. Inside this folder, open the default engine.ini file. This file contains our project settings that we modified through our editor. This includes the channels. Let's perform a search on this file. Search for the fighter channel. It should be the only result. On this same line of code, search for a portion of code that says channels equal. Whatever is to the right of this text is the actual channel value. Copy the value to... clipboard.
Okay, it just assigned like a number to it. Game trace channel 1. That's the fighter channel. Okay. And we use that in our component, in the logon component. Here.
Next, head back to the logon component file. We can paste the value after the double colon characters. Great, we're almost finished. The last parameter is the collision shape. Looking at the description for this parameter, it states that we can use a box, sphere, or capsule. We'll be using a sphere since we want to evenly check around the player for an enemy. So let's draw the sphere. Right above the function, let's define another variable called sphere with the F collision type. Let's set the value. To a function called makeSphere. This function requires a radius, which was set to 750. .0f. Let's pass this variable. Along to the function. You may be wondering, why are we using variables?
That doesn't seem to... Oh, F collision shape. I don't know why F. Collision shapes. Okay. Semicolon. Okay.
Can't we just pass these functions onto the sweep function? We could, but that doesn't look as clean. While not required, using variables can add clarity as to the type of values you're passing onto a function. The variable names are much more descriptive in my opinion. There's one more setting I want to add. In the fifth argument, we're searching for actors that have the fighter channel. However, the player also has this channel. Theoretically speaking, the player will be able to log onto this themselves, which we don't want. Luckily, this argument allows us to add a list of actors to ignore. The type is F collision query parameters. Let's define a variable above this function with this type. The name will be called ignore parameters. This type is a bit funky. It requires
a bit funky, he says. Here we go.
There's a bit of information. First, we have to provide a name by using the F name type. If you're not familiar with this type, it's a type for creating a string. The main difference between this type and a regular string is that this type will optimize the string and efficiently store it. This type accepts the text macro along with the actual string to store it. Let's call our query parameter ignore collision parameters. Next, we must tell this query if the tray should consider complex collision shapes. There are two types of collision shapes in Unreal, which are simple and the complex. Simple refers to shapes like capsules or boxes. Our player and bosses use simple collision shapes. The main advantage to using simple collision shapes is that they're pretty performance. However, accuracy tends to be a big problem with this type of shape. As an example, the image on the right shows how a player being dropped onto a chair causes them to fall off. On the other hand, complex collision shapes are designed to accurately reflect the mesh. If we apply a complex collision shape to the chair, dropping the player on it allows them to stand on it, as you can see from the image on the right. Luckily, we're using simple collision shapes.
Okay, so complex collision shapes are awesome, but they require a lot of power, I guess. So that's why we use the simple collision containers.
There really isn't the need to use complex shapes. The second value for this type is whether the trace should consider complex shapes. Let's pass it false since neither characters use complex shapes. The last value we must provide is the actor to ignore from the trace. For this value, we want to ignore the actor that's trying to lock onto a target. Luckily, we already know how to grab the current actor, which is by calling the getOwner function. That's all we have to do for this function. If you hover your mouse over it, there's actually an additional parameter. However, it's completely optional. How do I know that? Look closely at the parameters. There's an equal sign character after the parameter name.
Okay, that means there's a default value for it.
This indicates a default value is given to the parameter. As you can see, the last two parameters have default values, so if we don't pass in anything, the default values are used. In our case, the default values will suffice. There isn't a reason to override them. Alright, let's verify a target was hit. This function returns a Boolean value to tell us if we found the result. Let's store that value by defining a Boolean variable called B has found target.
Sure. Oh, wait. Bool has found B.
Let's wrap the function with a pair of curly brackets.
Right.
Next, add a conditional statement after the function. The condition will check if the variable is false. If it is, we'll return the function since we don't have any targets. If, on the other hand, if it does find a target, we'll let our logger run.
Okay, that makes sense. If not has found target, return.
Let's update the text by changing it to the following. Actor detected, %s. For this message, I want to log the actor's name, which is why we're using a placeholder. Let's pass in the actor's name with the following. Out result.getActor.getName. Every result is always going to have the actor accessible via the getActor function. From there, we can call any of the aActor functions. Whenever using string placeholders, we must pass them in as a reference. Add the asterisk character before the line of code. We're finished. Let's test our work. In Unreal, try compiling the code.
You compiling. Failed. Of course it does. Log on component 48. Get name. Oh, I need to pass a pointer to this. Crazy stuff, man. Well, I guess so. Okay. So now, when I press 1, 2, 3, 1, 2. Did I have 2 entries here? Huh.
Lastly, play the game. If we press the tab key, nothing happens because we aren't near the enemy. If I walk up to the enemy, their name starts to appear as I press the tab key. Awesome! We've successfully detected the enemy.
Output log. How can I dock? Okay.
Earlier we talked about default parameters for functions. Did you know we can add parameters to our Blueprint functions? By doing so, Unreal adds pins for them. So here's what I want you to do. Update the start lock on function to have a parameter called radius. Keep in mind, our function shouldn't be completely unconfigurable. We should allow our teammates to configure their settings. One setting we can allow for configuration is the radius of the sphere trace. When you create this parameter, give it a default value of 750, just like in our MakeSphere function. Lastly, update the MakeSphere function to use this parameter. I know we haven't gone over how to do this, but this is an opportunity for you to test how to add features in Unreal. It really is as simple as adding a parameter to the function. Unreal handles the rest. During this process, you might have to delete the node and re-add it for the changes to take effect. So give it a try and good luck. Adding a parameter to the function. Unreal handles the rest. During this process, you might have to delete the node and re-add it for the changes to take effect.
Oh, right, I need to add it to the header file as well. Okay, we're good. We're good. We go back. We compile. Compile complete. And we try this again. Output log. Log it. Okay, I have to re-edit. One here, right? Start log on. Delete. Call function start log on. Radius. Now I can give something bigger. Let me try 10,000. It doesn't seem to do anything. Why is that? Oh, started. Need to connect this. Okay. Compile, save, start. Okay. Try this again. Doesn't use that thing right now. Does it? Radius. I have to recompile.
Perfect. So give it a try and good luck. Alright, let's quickly bang this one out. Open the declaration file for the logon component. On the start logon function, add a float parameter called radius. We're using a float type because that's the type accepted by the MakeSphere function. Next, set the default value to 750.0f.
Oh, you do this in the header file?
Let's switch over to the C++ file. On the definition, add the radius parameter. You don't need to add the default value either.
Okay. So this should go into the header. Okay, this all saved. You recompile. Oops. What just happened? It here. Okay. Play. This works, but can we extend the parameter? Let me remove this. Call function start log on. Default 750. That's nice. Okay, we're good with this.
Lastly, let's update the MakeSphere function to use the radius parameter instead of hard-coding the number. Great, let's head on over to Unreal. First, we're going to delete the start logon node from the blueprint and save the file. Next, compile the entire codebase. Lastly, let's head back to the blueprint. We're going to re-add the logon node we previously deleted. After doing so, the node has the radius parameter with the default value. Awesome! Our designers will now be able to configure the radius in case they think the distance for locking onto an enemy is too small. Let's connect it with the start pin from the event node. Compile and save the file. Great, we've successfully detected our enemy. In the next lecture, let's work on modifying the camera to focus on them.
Okay, we are back.